Tonight, we're going to cross a line that cannot be uncrossed. There is a specific point in space where gravity stops being a force you could ever fight against. Cross it, and every path through space-time that was once open to you collapses into a single direction, inward, and you are never coming back. And here's what makes this stranger than anything else in physics. That boundary isn't made of matter. You can't see it. You can't feel it when you pass through it. It doesn't glow. It doesn't emit radiation. It doesn't push back against you. It's just a location in empty space where the geometry of reality quietly but permanently changes. By the end of tonight, you're going to understand exactly what that boundary is, why it exists, what it does to space and time on either side, and why crossing it means something so profound that it challenges everything intuition tells you about the universe we live in. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why that boundary exists at all, you first need to understand what gravity actually is. And the answer isn't what most people learned in school. Most people were taught that gravity is a force, an invisible pull between objects with mass. The sun pulls on Earth. Earth pulls on the moon. Masses attract each other across empty space. That description works well enough for everyday engineering and navigation. It is accurate enough to calculate the trajectories of spacecraft, to plan interplanetary missions, to land a probe precisely on a moving target tens of millions of miles away. But it is not what is actually happening. In 1915, Albert Einstein published his general theory of relativity. What he showed, through a decade of extraordinarily difficult mathematical work, was that gravity is not a force at all. It is a curvature of space-time. Mass doesn't pull on other mass through empty space. What mass does is warp the geometry of the space and time around it. Objects then move through that warped geometry, following what are called geodesics, the straightest possible paths through a curved landscape. And what we interpret as gravitational attraction is just the result of objects following those paths through geometry that has been distorted. This is not a metaphor. It is not an analogy designed to make complicated physics easier to understand. It is the actual mathematical structure of how gravity works. The curvature is real, measurable, and has been confirmed by experiment after experiment. Starlight bends around the sun during solar eclipses, exactly as Einstein's equations predict. GPS satellites in orbit have to correct for the fact that time runs faster in weaker gravitational fields, meaning the satellite's clocks gain time relative to clocks on the ground. If those corrections weren't applied, GPS navigation would accumulate errors of several miles per day. The relativistic time correction is not a theoretical nicety. It is built into the actual software running in your phone. When you drop an object, it isn't being pulled toward Earth by some mysterious attractive force reaching across empty space. It is following a path through curved space-time. The curvature created by Earth's mass just happens to point toward Earth's center. The object moves along the straightest path available to it through geometry that tilts in that direction. The more mass you have, the more space-time curves around it. A bowling ball curves space-time a tiny amount. Earth curves it more. The sun curves it more still. And a black hole where enormous mass has been compressed into an unimaginably small volume, curves space-time so severely that the geometry breaks down into something that has no equivalent anywhere else in the known universe. The concept of an object so massive that nothing could escape it is older than Einstein. In 1783, a British clergyman and amateur natural philosopher named John Michell was working through the implications of Newtonian gravity and the emerging understanding of light. He knew that a cannonball fired upward from Earth would slow down, stop, and fall back. The faster you fired it, the higher it would travel before turning around. Fire it fast enough, and it would escape entirely. That minimum speed, the speed above which an object can escape a body's gravity and never return, is called escape velocity. For Earth, the escape velocity is about 25,000 miles per hour. For the Sun, it is about 1,370,000 miles per hour. Michel asked a deceptively simple question. What if you had a body so massive and dense that its escape velocity equaled or exceeded the speed of light? Using the physics available to him, he reasoned that light would be unable to escape from such an object. It would be perpetually trapped. The object would be dark, invisible. He called them dark stars, and he published this idea in a paper for the Royal Society. The idea attracted little attention. It wasn't taken seriously by the broader scientific community, partly because light wasn't well understood at the time, and partly because the mathematics to explore it properly didn't yet exist. The idea faded. Then came Einstein. In 1915, he published the field equations of general relativity, and in 1916, just months after the publication, while serving on the Russian front during the First World War, a German physicist and astronomer named Carl Schwarzschild found an exact solution to those equations. He was working through the mathematics in whatever quiet moments he could find between the fighting. He sent the solution to Einstein in a letter, and Einstein was reportedly astonished by how quickly it had been found and by its elegance. Schwarzschild's solution described the geometry of space-time around a perfectly spherical, non-rotating, electrically neutral mass. It was a clean, exact result. But embedded in that solution was something unexpected. There was a critical radius, a specific distance from the center of any mass at which the mathematics produced a singularity. The geometry didn't just curve severely there. The equations produced infinite values. The metric, which is the mathematical object that encodes the geometry of space-time, broke down completely at that radius. Schwarzschild himself believed this was a mathematical artifact with no physical meaning. He thought that nothing in nature could actually be compressed small enough for that radius to fall outside the object itself. He was wrong. That critical distance is now called the Schwarzschild radius, and it exists for every object in the universe. Every single one, regardless of how ordinary it is. For Earth, the Schwarzschild radius is approximately 1/3 of an inch. That is the size to which you would have to compress the entire mass of Earth to create a black hole. All of it, squeezed into a sphere smaller than a marble. For the Sun, the Schwarzschild radius is about 1.9 miles. Squeeze all the Sun's mass into a sphere just under 4 miles in diameter, and you would cross the threshold. Under ordinary circumstances, none of this matters. Earth is not going to collapse into a black hole. The Sun is not going to collapse into a black hole. The Schwarzschild radius of these objects sits deep inside them, in a region where the matter of the object itself provides the pressure to resist further collapse. But when massive stars run out of nuclear fuel and their cores collapse under gravity, something different happens. The collapse is sudden and violent. In less than a second, the core of a dying star can go from something the size of Earth to something the size of a city. If the core is massive enough, roughly more than about 3 times the mass of the Sun after the collapse, then nothing stops it. Electron degeneracy pressure, the quantum mechanical resistance of electrons to being crowded together, is overwhelmed. Neutron degeneracy pressure, the same resistance applied to neutrons, is overwhelmed. Every known form of pressure fails. The collapse continues all the way down to a point of essentially zero volume and infinite density, which in mathematics is called a singularity. At that point, all the mass of the core sits inside a sphere far smaller than the Schwarzschild radius. A black hole exists, and surrounding it, at the exact Schwarzschild radius, is the event horizon, the invisible surface that defines the point of no return. The point in space where gravity becomes irreversible. The word horizon is chosen deliberately. A horizon in everyday life is a boundary beyond which you cannot see. Stand on a flat plane and look toward the edge of the world. You can see everything out to the horizon. Beyond it, the curvature of the planet hides things from your view. Events happening beyond the horizon are invisible to you, not because they're extraordinary, but simply because the geometry of the situation puts them out of reach. The event horizon of a black hole is similar in name only. The physical reality is far more fundamental. The event horizon is not a boundary beyond which you cannot see. It is a boundary beyond which events are causally disconnected from the rest of the universe. Not just invisible, causally disconnected. What that means requires a moment to properly absorb. In physics, 2 events are causally connected if one could have influenced the other. You can influence a future event if you can send a signal to it, a light beam, a radio wave, a gravitational disturbance, anything traveling at or below the speed of light. If you cannot send any signal between 2 events, they are causally disconnected. They cannot influence each other. Inside the event horizon, no signal of any kind can travel outward. Not light, not radio waves, not gravitational influences, not any form of information or energy. The reason is not that the signal encounters some barrier and gets blocked. The reason is geometrical. Inside the horizon, the structure of space-time is arranged so that all paths going outward are actually going inward. Space-time has been curved so severely that what you might call the outward direction simply doesn't exist anymore. There are no outward paths. Every path leads inward. The geometry of space-time has been rearranged so that inward is the only direction time flows. To understand what this really means, you need to know how physicists think about the structure of space-time around paths. In normal flat space-time, imagine yourself at a particular location at a particular moment. Every possible direction you could move, every possible path you could travel into the future, is contained within what's called your future light cone. Think of it literally as a cone opening upward from your current position. Light travels outward in all directions from your location, forming the surface of the cone. Any path you can travel must be inside that cone, because you can't move faster than light. Your future is everything inside and on the surface of that cone. As you approach a black hole, the intense curvature of space-time begins to tilt that cone. The cone itself, which represents all possible futures, starts rotating inward toward the black hole. More and more of the cone's interior is pointing toward the black hole's center. At the event horizon, the tipping is complete. The cone has been tilted so far inward that every possible future path, including the path light would take, trying to move directly away from the black hole, is pointing toward the singularity. The entire future light cone is aimed inward. There are no paths available that lead outward. Light, trying to escape from exactly at the event horizon, simply hangs there, suspended at the boundary, making no progress outward. Light slightly inside the horizon is moving inward, even if it's aimed in what locally seems like the outward direction. And for any massive object that has crossed the horizon, the situation is analogous to what we experience with time. You cannot stop time. You cannot reverse it. You cannot opt out of moving forward in time. You might move fast or slow through space. You might choose different locations. But the arrow of time carries you forward regardless of your preferences. Inside a black hole, the inward direction toward the singularity has the same character as the forward direction of time everywhere else. You will move toward the singularity, not because a force is pushing you, because inward is what future means inside the event horizon. The size of an event horizon depends entirely on the mass of the black hole. The relationship is direct and linear. Double the mass, double the Schwarzschild radius. A black hole, 10 times the mass of the Sun, has an event horizon about 18 miles across from one side to the other. A black hole, 100 times the mass of the Sun, has one about 180 miles across. A supermassive black hole with 1 million solar masses has an event horizon spanning about 3.7 million miles, roughly 4 times the distance from Earth to the Moon. A supermassive black hole with 1 billion solar masses has an event horizon spanning about 3.7 billion miles, which is roughly the size of Neptune's orbit around the Sun. These numbers scale upward cleanly. The most massive black holes discovered so far, the so-called ultramassive black holes at the centers of the largest and most ancient galaxies, contain tens of billions of solar masses. The black hole at the center of the galaxy TON 618, a quasar over 10 billion light-years away, has a mass of about 66 billion solar masses. Its event horizon has a radius of roughly 120 billion miles. An event horizon wider than the distance across our entire solar system, many times over. And yet, the event horizon of TON 618 is just a surface, an invisible geometric boundary in space. Not a physical structure, not a wall. Not matter of any kind. Just a place in space where the geometry has changed. This is the detail that surprises people most when they first encounter black hole physics. The event horizon is not a dramatic place locally. For a large enough black hole, you would not feel anything special as you crossed it. No dramatic force. No alarm. No visible boundary. The space-time curvature at the horizon of a supermassive black hole is actually quite gentle by local standards. The change in gravity across the length of your body what physicists call the tidal force, can be small enough that your body would feel nothing extraordinary. You could cross the event horizon of a sufficiently massive black hole and have absolutely no physical sensation that distinguishes that moment from any other moment during your infall. This is deeply counterintuitive. People imagine the event horizon as a dramatic threshold, a place where extreme forces announce themselves, where something physical prevents you from leaving. But there is no such announcement. There is no wall. There is no force at the boundary. The event horizon is not a thing you can touch or detect locally. It is a global property of the space-time geometry, a consequence of how the curvature is arranged on large scales. You have crossed the most absolute boundary in physics, and nothing in your immediate environment told you it happened. All the exits are gone. The universe outside continues exactly as it was, without any indication that something irreversible has just occurred. For a smaller black hole, the situation at the horizon is different. A stellar mass black hole of 10 or 20 solar masses has a much smaller event horizon, and the tidal forces there are extreme. The difference in gravitational pull between your head and your feet, across the roughly 6 feet of your body, would be catastrophically large. This differential tearing force, which physicists sometimes call spaghettification, would stretch your body vertically and compress it horizontally, pulling you apart into a long, thin strand of matter and energy. For a small enough black hole, this process begins well before you reach the event horizon itself. The tidal forces would be lethal, far outside the boundary. But this is a feature of the size, not the horizon itself. For the supermassive varieties, the horizon is quiet. The violence comes later, as you approach the singularity deep inside. Now we need to understand what the event horizon does to time. Time is not what most people think it is. It is not a fixed, universal, absolute quantity that flows at the same rate everywhere. This is one of the things Einstein's relativity made unmistakably clear. Time is relative. It passes at different rates depending on where you are and how you're moving. Specifically, time runs slower in stronger gravitational fields. This is called gravitational time dilation, and it has been measured and verified in experiments that leave no room for doubt. The GPS satellites orbiting Earth are in a region of weaker gravity than the ground. Their clocks run faster than clocks on Earth's surface. The difference is about 45 microseconds per day from gravitational time dilation. There's also a competing effect from their velocity, which makes their clocks run slower by about 7 microseconds per day. The net result is that GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. This is not a small effect in the context of precision navigation. Accumulated over a day, without correction, this error would cause positional errors of several miles. The correction is applied continuously and automatically. It works because Einstein's relativity is correct. This is the first thing to hold on to. Now apply gravitational time dilation near a black hole. As you fall toward the event horizon, time dilation becomes increasingly severe. Your clock, from the perspective of a distant observer watching you, runs slower and slower. An observer far away from the black hole, watching you fall with a very powerful telescope, would see your movements gradually slow. Your light becomes increasingly redshifted as it has to climb out of the deepening gravitational well to reach them. The redshift becomes more and more extreme as you approach the horizon. At the horizon itself, the time dilation becomes infinite. From the distant observer's perspective, your clock would appear to stop entirely. You would appear to freeze. Your image would dim and redden as your light becomes stretched to longer and longer wavelengths, eventually fading from visible to infrared to radio, until you effectively vanish from detectability. You appear to the outside universe to hover at the event horizon forever, frozen in time. You never appear to cross. From the outside universe's perspective, nothing ever actually falls through an event horizon. Everything appears to freeze at the boundary, gradually fading from view. But from your own perspective, inside your own reference frame, none of this is happening. You fall through the horizon in a finite and sometimes quite short amount of your own time. Your clock ticks normally. You feel no extraordinary slowing. You experience no freezing. You cross. And this is where general relativity requires you to set aside the intuition that there must be one true account of what happened. Both descriptions are real. Both are accurate. The frozen at the boundary account is what the distant observer genuinely measures using real clocks and real instruments. The falls through normally account is what the infalling observer genuinely experiences using their own real clocks. General relativity tells us that there is no single universal description that all observers agree on. Different reference frames can disagree profoundly about sequences of events, about simultaneity, about what happens when. The event horizon makes this maximally vivid. Two observers start with a shared history, then one crosses the horizon, and from that point forward, their descriptions of reality diverge completely and can never be reconciled. Because no signal can carry information from one to the other. In 1963, a New Zealand mathematician named Roy Kerr found a new solution to Einstein's field equations. Schwarzschild's solution described a non-rotating black hole. Kerr's solution described something more realistic, a rotating one. In nature, virtually everything rotates. Stars rotate. Planets rotate. Galaxies rotate. When a massive star collapses, the rotating core doesn't stop rotating. Conservation of angular momentum means the rotation speeds up dramatically as the core shrinks, the same way a spinning figure skater spins faster when they pull their arms in. A collapsing stellar core goes from perhaps one rotation per month to potentially hundreds of rotations per second. The result is a black hole that is spinning, sometimes at a significant fraction of the maximum rate that physics allows. The Kerr solution, which describes the geometry of space-time around such a rotating mass, is considerably more complex than Schwarzschild's. A rotating black hole has not one event horizon, but two. The outer event horizon is the point of no return in the sense we've been discussing. Cross it, and you cannot return to the outside universe. The inner horizon is a second boundary, deeper inside, where the nature of space-time changes, again in ways that our current understanding does not fully resolve. The physics near the inner horizon is connected to some of the deepest unresolved questions in theoretical physics, relating to stability and what an infalling observer would actually experience. But there's another feature of the Kerr solution that has no counterpart in the Schwarzschild case. It is called the ergosphere. The ergosphere surrounds the outer event horizon like a flattened bubble, extending outward from the poles and bulging at the equator. It sits outside the event horizon and is therefore not a region of no return. Things can enter the ergosphere and leave. But inside the ergosphere, space-time itself is dragged around by the black hole's rotation. This effect is called frame dragging, and it exists outside the ergosphere too. Any rotating mass drags space-time around with it, pulling local inertial frames into rotation. Earth does this, but so weakly it is barely measurable. A rapidly rotating black hole does it so dramatically that inside the ergosphere it is impossible to remain stationary. Even if you fired your rocket engines with maximum thrust in the direction opposite the black hole's rotation, trying to hold your position, you would still be dragged around. Space-time itself is moving, carrying you with it. Everything inside the ergosphere must orbit the black hole. Not because a force is pushing it, because the geometry says orbital motion is the only option. The ergosphere has a consequence that at first sounds like it shouldn't be possible. Because it is outside the event horizon, it can in principle be used to extract energy from the rotating black hole. This is called the Penrose process, described by physicist Roger Penrose in 1969. The basic idea is that you send an object into the ergosphere and have it split into two pieces in precisely the right way. One piece falls inward, past the event horizon. The other piece escapes outward. If the geometry and the splitting are arranged correctly, the escaping piece can emerge, carrying more energy than the original combined object brought in. The extra energy comes from the black hole's rotational energy. The black hole slows down slightly. Energy has been extracted. The Penrose process doesn't happen spontaneously in nature in any simple way, but it is consistent with all the known laws of physics. It means that rotating black holes are not purely passive sinks that absorb everything and return nothing. They are objects with rotational energy that can, in principle, be tapped. Astrophysicists believe that some variation of this process, involving magnetic fields and the accretion of matter, is responsible for the enormous jets of particles that many active black holes produce. Jets that can extend for millions of light years and rival entire galaxies in luminosity. The event horizon and the ergosphere working together, in other words, can be the engine driving some of the most energetic phenomena in the observable universe. The first direct image of a black hole was released on April 10, 2019. The Event Horizon Telescope collaboration, a network of radio observatories spread across the entire planet and functioning together as a single Earth-sized telescope, produced an image of the region around the supermassive black hole at the center of Messier 87. Messier 87 is a giant elliptical galaxy about 54 million light-years away in the constellation Virgo. Its central black hole contains about 6.5 billion solar masses. Getting to that number required years of careful work using multiple observation techniques, tracking the motions of stars and gas orbiting the black hole, measuring the brightness and shape of the accretion disk, cross-checking with independent methods. The event horizon radius implied by that mass is about 12 billion miles, larger than the orbit of Saturn in our solar system. an enormous volume by human intuition. But remember, the Milky Way alone spans 100,000 light-years. Even the event horizon of this extraordinary object is a point by galactic standards. What the image shows is not the event horizon directly. You cannot photograph something from which no light escapes. What it shows is the shadow the black hole's event horizon casts against the glowing ring of hot gas orbiting around it. That gas, the accretion disk, is falling inward toward the black hole. It has been compressed and heated by the intense gravity to temperatures of billions of degrees. It radiates brilliantly in radio frequencies. And in the center of that glowing ring, there is darkness. Not the darkness of empty space. The darkness of an absence of light produced by a geometry that redirects all light inward. The shadow. The image showed an asymmetric ring, brighter on one side than the other. This asymmetry is a real physical effect. The gas on the side of the disk, orbiting toward us, is blue-shifted, its radiation boosted in brightness by its motion. The gas, orbiting away from us, is red-shifted and dimmed. The result is a lopsided ring. And that lopsidedness, that specific pattern of brightness, was exactly what Einstein's equations predicted it would look like. The image was a verification of general relativity in an extreme regime that had never before been directly observed. Producing that image required coordinating observations across telescopes in Antarctica, Chile, Hawaii, Spain, Mexico, and Arizona. The observations had to happen simultaneously during a narrow window when weather conditions at all sites were favorable. The data from each site was recorded on specialized hard drives and physically shipped to processing centers because the volume of data made network transfer impractical. Petabytes of information had to be synchronized and analyzed before the image could be assembled. The entire project was a technical achievement of the first order. 3 years later, in 2022, the same collaboration released an image of the second black hole they had targeted, Sagittarius A, at the center of our own Milky Way. Sagittarius A sits 26,000 light-years from Earth. It contains about 4 million solar masses. Its event horizon has a radius of about 7.4 million miles. Getting that image was significantly harder than Messier 87's. Because Sagittarius A is much smaller, gas orbiting near its event horizon completes an orbit in minutes rather than the days it takes for gas near Messier 87. The image was shimmering and changing on short timescales. The team had to develop new techniques to handle this variability, averaging and reconstructing thousands of snapshots to produce a stable final image. But they got it. The same structure, a bright ring surrounding a dark shadow, 2 event horizons photographed, 2 points of no return made visible in their way for the first time. In 1974, Stephen Hawking published a result that changed the way physicists think about black holes. Before his paper, black holes were understood as purely absorbing objects. Mass, energy, and information could fall in. Nothing could come out. They were cold, dark, silent. Objects defined entirely by what they consumed. Hawking showed that this picture is incomplete. Quantum mechanics changes it. Empty space, in quantum mechanics, is not truly empty. The vacuum is filled with constant quantum fluctuations. Pairs of particles and their antiparticles continuously appear from the vacuum, exist for a fleeting moment, and then annihilate each other, returning their borrowed energy to the vacuum. This is called virtual particle production, and it happens everywhere in space, all the time. Normally, the pairs annihilate almost immediately and leave no lasting effect. But near the event horizon of a black hole, something different happens. A particle pair appears right at the horizon. One member of the pair finds itself just inside the horizon. The other finds itself just outside. They can no longer meet to annihilate because the horizon separates them. The inside particle falls inward toward the singularity. The outside particle escapes outward into space. From the perspective of an observer far from the black hole, it looks as though the black hole is spontaneously emitting a particle. Energy has been radiated away. This is Hawking radiation. The temperature of this radiation depends on the black hole's mass. Specifically, the Hawking temperature is inversely proportional to the mass. For a stellar mass black hole of 10 solar masses, the Hawking temperature is about 6 billionths of a degree above absolute zero. This is far colder than the cosmic microwave background radiation that fills all of space, which has a temperature of about 2.7 kelvins. Hawking radiation from stellar mass black holes is undetectable against that background. It's not that we lack sensitive enough instruments. It's that the signal is genuinely swamped by the ambient temperature of the universe itself. For a supermassive black hole of 1 billion solar masses, the Hawking temperature is even lower. Essentially, unmeasurably close to absolute zero. But for smaller black holes, the temperature rises. A black hole with the mass of a mountain would radiate at visible temperatures. A black hole with the mass of a large asteroid would be hot enough to be intensely luminous. And a microscopic black hole, if such a thing could exist, would be so hot that it would radiate explosively, shrinking rapidly and ending in a burst of high-energy radiation. The key implication of Hawking radiation is that black holes slowly lose mass. They emit energy, and because mass and energy are equivalent through the relationship E equals mc squared, this means they're converting their mass into radiation. For large black holes, this process is extraordinarily slow. A black hole with 10 solar masses would take something like 2 × 10⁻⁶ years to evaporate completely through Hawking radiation. For comparison, the current age of the universe is about 13.8 billion years. The number 2 × 10⁻⁶ is incomparably larger. But the process is real. It happens. And as a black hole loses mass and shrinks, the Hawking temperature rises. A shrinking black hole radiates faster, shrinks faster, raises its temperature further, radiates even faster. In the final moments of a black hole's life, the process accelerates into an explosive final burst. The event horizon shrinks to nothing. And then it's gone. What happened to everything that fell in? This question is not trivial. It is one of the central unresolved problems in theoretical physics, and it has been for over 50 years. When matter falls into a black hole, it carries information. The information about what it was made of, how its atoms were arranged, what quantum state it was in. Every physical system carries information of this kind. Quantum mechanics says, in very precise mathematical terms, that information cannot be destroyed. This is not a principle physicists chose to adopt because it seemed philosophically satisfying. It is a consequence of the mathematical structure of quantum mechanics. The equations that describe how quantum systems evolve over time have a specific property called unitarity, which ensures that information is always conserved. You can scramble information. You can distribute it across many particles. You can make it extremely difficult to recover. But you cannot destroy it. General relativity, on the other hand, produces a picture in which black holes that evaporate via Hawking radiation appear to destroy information. All black holes of the same mass, angular momentum, and electric charge produce identical Hawking radiation. The radiation contains no information about what fell in. Throw in a star. Throw in a library. Throw in a handful of elementary particles. You get the same featureless thermal radiation back. When the black hole finishes evaporating, that information appears to be gone. No encoding of it survives in the outgoing radiation. This is the black hole information paradox. It is a conflict between two theories that are each individually extraordinarily successful. General relativity has passed every experimental test applied to it. Quantum mechanics has passed every experimental test applied to it. But they appear to give contradictory answers to what happens to information inside a black hole. Hawking himself initially believed that information was genuinely lost, that black holes represented a real exception to quantum mechanical unitarity, that the universe would simply have to live with this. He later changed his view, accepting that information probably escapes somehow, but the question of how remained open. The problem is that any mechanism for information escape has to contend with the fact that nothing can travel outward through the event horizon. If information escapes in the Hawking radiation, it cannot do so by simply climbing through the horizon. The horizon is the definition of the barrier to such escape. Some mechanism must exist that encodes the information in the outgoing Hawking radiation without violating the geometry of the event horizon. Working out that mechanism in a mathematically precise and consistent way has been the project of a significant fraction of theoretical physics for decades. In recent years, progress has been made using a framework called the island formula. This approach, drawing on deep connections between quantum mechanics and the geometry of space-time, suggests that information is indeed encoded in the Hawking radiation, but through a subtle and non-local mechanism that doesn't require information to climb through the horizon in any simple sense. The full picture is still being worked out. The mathematics is intricate. The physical interpretation is debated. But the weight of current theoretical evidence seems to be moving toward the view that information escapes. The event horizon, which appears to destroy information from the outside, somehow does not actually destroy it. The mechanism by which this happens remains one of the deepest open questions in physics. There is a related crisis that emerged from a careful analysis of what information escape would require. In 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that became known by the initials of their names, AMPS. They worked through the logical consequences of requiring that information escape from black holes in Hawking radiation. And they found that those consequences were alarming. Quantum mechanics requires that the Hawking radiation emitted at different times must be quantum mechanically entangled with each other in the right way to carry information outward. But there's a rule in quantum mechanics called the monogamy of entanglement, which says that a particle can only be maximally entangled with one other thing. If the early Hawking radiation is entangled with the late Hawking radiation in the way needed for information to escape, then it cannot also be entangled with the matter that fell into the black hole. But if it's not entangled with the matter that fell in, then the quantum state of the matter inside the black hole is completely disconnected from the quantum state of the radiation outside. And the mathematical structure of quantum field theory, which describes how particles behave near the event horizon, seems to require that such a disconnection would be accompanied by a burst of extremely high-energy radiation right at the horizon, a firewall. Rather than crossing the horizon smoothly and unremarkably, as general relativity predicts, an infalling observer would encounter an effectively solid wall of intense radiation. The event horizon in this picture would not be a quiet boundary. It would be a place of violent destruction. The Amps firewall paradox put three foundational principles of physics into apparent conflict. General relativity says the event horizon is locally unremarkable. Quantum mechanics says information must be conserved. The equivalence principle, one of the cornerstones of general relativity, says that a freely falling observer should not be able to distinguish free fall from floating in empty space. A firewall violates the equivalence principle. All three of these principles cannot simultaneously be true if the firewall analysis is correct. At least one of them has to be modified or abandoned. Physicists disagree on which one. Some accept the firewall and look for ways to modify our understanding of the event horizon. Others believe the firewall resolution will require new physics that doesn't yet exist. Others argue that the paradox reveals that the interior of a black hole is not an independent region of space-time, but is somehow encoded on or equivalent to the exterior, an idea related to the holographic principle. What is not in dispute is that the event horizon sits precisely at the fault line between our two most successful theories of physics. The point in space where gravity becomes irreversible is also the point where our current understanding of the universe strains to its limits. The holographic principle is an idea that grew directly from thinking carefully about what the event horizon means. In the early 1970s, when Stephen Hawking was working out the thermodynamics of black holes, he found a remarkable relationship. Working with a physicist named Jacob Bekenstein, he established that black holes have entropy. Entropy is a measure of the information content of a physical system. For ordinary objects, entropy is proportional to the number of ways the object's constituents could be arranged while still producing the same macroscopic appearance. More particles, more possible arrangements, more entropy. And entropy, for ordinary objects, scales with volume. A box twice as big has twice the volume and can hold twice as many gas molecules, and so has roughly twice the entropy. But for a black hole, Hawking and Bekenstein found that the entropy is proportional not to the volume of the black hole, but to the area of its event horizon. The Bekenstein-Hawking entropy formula states that the entropy equals the area of the event horizon divided by 4 times the square of the Planck length. The Planck length is about 1.6 times 10 to the negative 35 meters. It is the smallest length scale at which our current theories of physics are expected to be reliable. At that scale, quantum effects of gravity become significant, and our understanding breaks down. The Bekenstein-Hawking formula says that each unit of Planck area on the event horizon corresponds to 1 bit of information about the black hole's interior. All the information that describes everything inside the black hole, all the matter and energy and quantum states that have ever fallen in, is encoded on the surface of the event horizon, not in the volume. On the surface. This is the first hint of the holographic principle. It suggests that the 3-dimensional interior of a black hole is, in some deep sense, described completely by the 2-dimensional surface surrounding it. A physicist named Gerard 't Hooft and independently Leonard Susskind generalized this into a broader conjecture. Perhaps this is a general feature of physics. Perhaps all the information in any volume of space is encoded on a surface surrounding that volume. The universe might be fundamentally holographic in nature. The most mathematically precise realization of this idea came from Juan Maldacena in 1997. Maldacena discovered a precise mathematical equivalence called a duality between a theory of gravity in a particular type of curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. The two theories, one with gravity in the bulk and one without gravity on the boundary, describe exactly the same physical reality. Every calculation in one corresponds to an equivalent calculation in the other. This is called the anti-de Sitter, conformal field theory correspondence, or ADS, CFT for short. It is one of the most influential theoretical results in physics of the past 3 decades. It has been used to study strongly coupled quantum systems, plasma physics, condensed matter systems, and the behavior of black holes. And it started from the event horizon. From asking what it means that a black hole encodes all its information on a surface. From the strange fact that the boundary counts as much as the interior. The event horizon is not just a geometric feature of a massive object. It may be a window into the deepest structure of reality, into a universe where surfaces and volumes, where 2 dimensions and 3 dimensions are not as distinct as they seem. In addition to stellar mass and supermassive black holes, physicists have proposed a third category: primordial black holes. These would be black holes formed not from collapsing stars, but from the extreme density fluctuations in the very early universe. In the first fractions of a second after the Big Bang, the universe was a hot, dense plasma, compressed to extraordinary densities. Small regions, slightly denser than average, could have collapsed directly into black holes under their own gravity, without the intermediate step of forming stars first. The mass of a primordial black hole would depend on the specific conditions when it formed, and could range from the mass of a large asteroid to many solar masses or more. Primordial black holes, with masses smaller than about 10 to the 12 kilograms, would have evaporated via Hawking radiation by now. The Hawking temperature for such small objects is high enough, and the evaporation rate fast enough, that they would not survive to the present day. But more massive primordial black holes could still exist, and they have attracted attention as a possible component of dark matter. Dark matter is the name for whatever provides the extra gravitational force that holds galaxies and galaxy clusters together beyond what ordinary visible matter can explain. It comprises about 85% of all the matter in the universe. It does not emit, absorb, or reflect light. We infer it entirely from its gravitational effects. If even a fraction of this dark matter consists of primordial black holes, there would be event horizons scattered throughout the cosmos. Ancient boundaries between the accessible universe and irreversible gravity, present since nearly the beginning of time. Searches for primordial black holes are ongoing. One approach is gravitational microlensing. When a compact, massive object, including a black hole, passes in front of a distant star, it acts as a gravitational lens, bending the star's light and causing it to temporarily appear brighter. The pattern and duration of this brightening depends on the mass of the lensing object. Surveys of millions of stars looking for this characteristic brightening have constrained how many primordial black holes can exist in certain mass ranges. So far, the results have ruled out some mass ranges as the dominant component of dark matter, but left others open. The search continues. There are objects that sit just outside the boundary of becoming a black hole, and they are extraordinary in their own right. Neutron stars. When a stellar core collapses and the remaining mass is between roughly 1 and 3 solar masses, the collapse halts at a different threshold. Rather than continuing all the way to a singularity, the collapse is stopped by neutron degeneracy pressure. Neutrons, like electrons, resist being packed too closely together due to the Pauli exclusion principle, a quantum mechanical rule that prevents identical fermions from occupying the same quantum state. The resulting object is a neutron star. Neutron stars are remarkable by any measure. They typically contain about 1 to 2 solar masses compressed into a sphere roughly 12 to 15 miles in diameter. This density is so extreme that a single teaspoon of neutron star material weighs approximately 10 billion tons. Gravity at the surface of a neutron star is about 200 billion times stronger than gravity at Earth's surface. Neutron stars rotate. They rotate very fast. As the stellar core collapses, conservation of angular momentum spins them up from their original leisurely rotation to rates of up to hundreds of revolutions per second. Some neutron stars emit beams of electromagnetic radiation from their magnetic poles, and as they rotate, those beams sweep across space like cosmic lighthouses. When such a beam happens to sweep past Earth with each rotation, we detect it as a regular pulse. These are called pulsars. Pulsars are among the most precise natural clocks in the universe. The timing of their pulses is so regular that any deviation can be measured with extraordinary precision, allowing them to be used as tools for testing general relativity and even for detecting gravitational waves. The key distinction between a neutron star and a black hole is that a neutron star has no event horizon. It has a surface. Things that fall onto a neutron star hit the surface. Light can escape from a neutron star. There is no point of no return, at least not in the same sense. But neutron stars exist right at the edge. If you added enough mass to a neutron star to push it above the maximum mass that neutron degeneracy pressure can support, typically thought to be somewhere between 2 and 3 solar masses, 214, the collapse would resume. neutron degeneracy pressure would be overcome. The collapse would proceed all the way to a singularity. An event horizon would form. The neutron star would become a black hole. This transition can happen through mass accretion, where a neutron star in a binary system slowly pulls matter from its companion until it becomes too massive. Or it can happen through a violent collision, when two neutron stars in a binary spiral together and merge. In August 2017, the LIGO and Virgo gravitational wave detectors simultaneously detected the gravitational waves from two merging neutron stars. The event happened about 130 million light-years away. The gravitational wave signal arrived at Earth after traveling that distance. Within seconds, telescopes across the planet were pointed at the source. An extraordinary explosion was seen. A kilonova, the spectacular electromagnetic fireworks produced when two neutron stars collide and merge. The kilonova produced enormous amounts of heavy elements: gold, platinum, uranium, all the elements heavier than iron that cannot be produced in ordinary stellar burning. They were forged in the nuclear physics of the collision. And then, at the end of that violence, the merger product collapsed. It exceeded the maximum mass that neutron degeneracy pressure could support. An event horizon blinked into existence 130 million light-years away. The birth of a new black hole, marked simultaneously by the most dramatic electromagnetic display and the first multi-messenger gravitational wave event ever detected. The gold in your jewelry, the platinum in the catalytic converter of a car, the uranium in nuclear reactors, all of these began their existence in events like that one, forged in the moment, surrounding the formation of an event horizon. The point of no return was the punctuation mark at the end of a sentence written in the most energetic physics the universe produces. The event horizon also has a face that looks outward. From the perspective of someone watching the black hole, not falling into it. An outside observer with a telescope pointing it at a black hole sees things that general relativity predicted and that observations have confirmed. The light from objects near a black hole is gravitationally lensed. The warped space-time bends the paths of light beams, magnifying distant objects, creating multiple images of the same source, and producing arcs and rings of light. This is the same effect that makes galaxy clusters act as gravitational lenses for more distant galaxies behind them, something seen in many famous Hubble Space Telescope images. But near a black hole, the effect is far more extreme. Light bending at such dramatic angles creates structures that don't exist anywhere else. The photon sphere is the most striking example. This is a region outside the event horizon, where gravity is strong enough for light to travel in circular orbits. For a non-rotating black hole, the photon sphere sits at 1.5 times the Schwarzschild radius, 1.5 times as far from the singularity as the event horizon itself. At the photon sphere, a photon can orbit the black hole indefinitely, going around and around in a circle. These orbits are unstable. A photon exactly at the right distance can orbit, but the slightest perturbation either sends it spiraling inward to be captured or sends it spiraling outward to escape. The photon sphere is the gravitational equivalent of a mountain peak that is perfectly flat at the top. You can balance there, but any tiny nudge rolls you off in one direction or the other. There is no stable resting position. The photon sphere is responsible for one of the most striking aspects of black hole images. When the Event Horizon Telescope looked at Messier 87, it was seeing photons that had originated in the accretion disk and been bent by gravity into the configuration of the image. Light from the disk behind the black hole was bent around it and arrived at telescopes on the opposite side. Light from the top of the disk was bent downward. Light from the bottom was bent upward. Light from the sides curved around to fill in the ring. The bright ring in the image is light from the photon sphere region and the accretion disk bent by gravity into a luminous ring as seen from Earth. The dark region in the center, the shadow, is actually larger than the event horizon itself. It is roughly 2.5 times the event horizon radius. The shadow is created by the fact that any photon aimed at the event horizon or aimed close enough to it to spiral inward never reaches an outside observer. The shadow represents all the angles from which no photons reach us. The event horizon is inside that shadow, hidden within a darkness that is itself created by the geometry of space-time around the horizon. The event horizon is invisible within the invisible. There is a category of objects so extreme that they challenge the distinction between a black hole and a supermassive core. Ultramassive black holes at the centers of the largest ancient galaxies have masses in the tens of billions of solar masses. The galaxy Home 15A times hosts a black hole of roughly 40 billion solar masses. Its event horizon has a radius of about 123 billion miles. That single geometric boundary, the invisible surface marking the point of no return, encloses a volume wider than our entire solar system many times over. Nothing physically dramatic marks that boundary from the inside. Gravity there, at the horizon of a 40 billion solar mass black hole, is extraordinarily mild by comparison to its mass. The tidal forces at the horizon are so gentle that a human body would barely notice them. You could be falling through the event horizon of that black hole several billion years after its formation and feel nothing more dramatic than floating in empty space. There would be no announcement, no signal. Nothing that told you the most consequential crossing in the universe had just occurred. The contrast between the enormity of what that boundary means, the permanent severance from the entire rest of the universe, and the complete physical gentleness of the moment of crossing is one of the most philosophically striking facts in all of physics. Significance and sensation have been completely decoupled. The most absolute boundary has zero local physical signature. We need to talk about what happens as you continue falling after crossing the horizon, specifically as you approach the singularity. For a non-rotating Schwarzschild black hole, the mathematics of general relativity says that after crossing the horizon, the singularity is not in a place. It is in the future, in a genuinely literal sense. Outside the horizon, the singularity is in a spatial direction, toward the center. You can avoid it by not going that way. But inside the horizon, the structure of space-time is such that the singularity is ahead in time, not ahead in space. It is where time goes. You cannot avoid the singularity any more than you can avoid tomorrow. The time between crossing the horizon and reaching the singularity is finite. It depends on the mass of the black hole. For a stellar mass black hole of 10 solar masses, the proper time between crossing the horizon and reaching the singularity is a tiny fraction of a second, much shorter than the time it would take to react to anything. Tidal forces would have already destroyed a human body well before the horizon crossing for such a small object. But setting that aside as a matter of scale, for a supermassive black hole of 1 billion solar masses, the proper time between crossing the horizon and reaching the singularity is on the order of hours to perhaps a day. Enough time to do science if the tidal forces are survivable, which, for a sufficiently massive black hole, they might be near the horizon. You would have time to observe the interior. Time to try to make measurements of what can only be seen from inside. To see physics that no observer outside has ever or could ever see. And then the singularity approaches. General relativity says it is a point of infinite density and infinite curvature. But almost no physicist believes that general relativity is telling the truth at that point. The infinite values are signals that the theory has reached its limits. The actual physics of the singularity requires a theory of quantum gravity, and we don't have one. Not a complete, tested, reliable one. String theory offers predictions. Loop quantum gravity offers different ones. Other approaches offer still others. What most of them share is the expectation that the singularity is not actually a singularity. That at the Planck scale, the extreme density does not go to infinity. Something else happens. The fabric of space-time itself undergoes some quantum transformation. Maybe a bounce. Maybe a transition to a different phase. Maybe something entirely without analogy in our current conceptual vocabulary. The interior of a black hole, past the event horizon, past the point of no return, is the only place in the known universe where physics would give us an unobstructed view of quantum gravity. If only we could reach it and come back. We cannot come back. The event horizon forbids it. Whatever is learned inside stays inside. The most extreme laboratory for fundamental physics is permanently inaccessible to any external observer. This is either deeply frustrating or deeply fitting, depending on how you think about it. The boundary that marks the limit of what we can physically reach from outside is also precisely the boundary that marks the limit of what our current theories can describe from inside. The event horizon is the edge of the known universe in a very precise sense. Not the edge of what exists. The edge of what can reach us, and the edge of what our theories reliably describe. There is one more aspect of the event horizon worth dwelling on. The way it changes over time from the outside. A black hole is not static. It grows when it swallows matter. The event horizon expands. Each time gas falls in from the accretion disk, each time a star passes too close and gets torn apart by tidal forces in a process called a tidal disruption event, the mass of the black hole increases. The Schwarzschild radius increases proportionally. The event horizon pushes outward, expanding to accommodate the new mass. There is a theorem in general relativity called the area theorem, proven by Stephen Hawking in 1971. It states that the total surface area of all event horizons in the universe cannot decrease over time. In any interaction or merger involving black holes, the combined area of the event horizons afterward must be at least as large as the combined area before. This theorem has a deep connection to thermodynamics. In thermodynamics, there is a law called the second law, which states that the total entropy of a closed system cannot decrease. The resemblance between the area theorem and the second law is not a coincidence. Black hole entropy, The Bekenstein-Hawking entropy, proportional to the event horizon area, makes the connection precise. The entropy of black holes, measured by their horizon area, behaves exactly like thermodynamic entropy. It can increase. It can stay the same. It cannot spontaneously decrease. This is one of the most beautiful unifications in physics. An abstract geometric object, the area of an invisible surface in space-time, obeys the same fundamental law as the entropy of a cup of coffee cooling on a table. The universe applies the same accounting rules to the largest and the smallest, to the event horizon of a supermassive black hole and to the atoms in a gas. When Hawking radiation was added to the picture, the situation became more subtle. Hawking radiation carries energy away from the black hole. The black hole loses mass. The event horizon shrinks. The area decreases. This seems to violate the area theorem. But the area theorem was derived from classical general relativity before quantum effects were included. When you account for the entropy of the Hawking radiation itself, adding it to the entropy of the black hole's horizon, the total entropy, horizon plus radiation, still increases. The second law is preserved. The accounting just has to be done more carefully when quantum effects are included. This generalized version is sometimes called the generalized second law of thermodynamics. It holds even when black holes are evaporating. The universe insists on it. By now, we have covered the event horizon from nearly every angle available to current physics. The geometry that creates it, the mass scales that produce it, what it does to time, to information, to the paths of particles, the rotating case and the ergosphere, the photon sphere that creates the black hole's shadow, the conflict with quantum mechanics over information, the firewall paradox, the holographic principle, Hawking radiation and thermodynamics, primordial black holes and neutron stars, the images captured by the Event Horizon Telescope, and yet the event horizon resists being fully understood. Every angle we approach it from reveals a new tension, a new question, a new place where the physics strains. This is not a sign that the science is weak. It is a sign that the event horizon is sitting at the precise location where the universe is telling us that our current theories are incomplete, that something beyond what we know is waiting to be discovered. The event horizon is not just an interesting feature of extreme astrophysics. It is a pointer, a landmark, a place in the universe where physics has left a note saying, "Here is where the current understanding ends. Here is where the next revolution will have to begin." Physicists have been working on that revolution for over a century. They are still working on it. The event horizons of the universe are waiting patiently. Think about what it means that these boundaries are real, not theoretical, not speculative. They exist right now, surrounding every collapsed stellar remnant massive enough to have made the crossing, surrounding every supermassive concentration at the center of every large galaxy we can observe. Sagittarius A, at the center of our own Milky Way, is sitting 26,000 light-years from where you are. Its event horizon is a sphere about 14.8 million miles in diameter. At this moment, while you're reading this, while you breathe and think and go about whatever your day is, matter is spiraling into it through the accretion disk. Stars are orbiting it at thousands of miles per second. Space-time is curved severely in its vicinity. Time is passing more slowly there than here, and the boundary of its event horizon is sitting quietly in the dark, doing exactly what it always does, existing as the most absolute edge in the universe, not asking anything of the space around it, not announcing itself, just being the line past which the future has only one direction. Everything that has ever crossed that specific boundary has gone somewhere we cannot follow. A star that wandered too close 1,000,000 years ago. Gas from a molecular cloud that fell in 10,000 years ago. A stray particle that crossed the threshold a second ago. All of them moved through the same invisible surface. All of them continued on inside. None of them could send a message about what they found. The universe has arranged itself so that the most extreme place it contains is the one we are least able to study from the outside. The one place where the physics changes most dramatically is the one place from which no observer can return to tell us. And that boundary, that irreversible edge, has been imprinted on space-time itself in every corner of the observable cosmos. Tens of billions of galaxies, most of them with supermassive black holes at their centers. Each one surrounded by an event horizon, a geometric surface encoding the maximum entropy of its interior. A boundary that thermodynamics honors, that quantum mechanics struggles with, that general relativity describes, but does not fully explain. A point in space where gravity stopped negotiating a long time ago. There is a phenomenon connected to the event horizon that is so extreme it barely seems like physics anymore. It is called a tidal disruption event. Stars in the central regions of galaxies don't just fall quietly into the black hole. The vast majority of them never come close. They orbit the supermassive black hole the same way stars orbit any other massive concentration of mass, maintaining stable orbits for billions of years. But occasionally, a star's orbit is perturbed. It might be nudged by the gravitational influence of another nearby star. It might be scattered by a close encounter. It might wander too close to the edge of a stable orbit. And when a star gets close enough to a supermassive black hole, something extraordinary and violent happens. Not because it crosses the event horizon, but because the tidal forces become strong enough to overcome the star's own gravity. Every star is held together by gravity. The gas and plasma that make up the star are attracted to each other, to the center of mass of the star itself. That self-gravity is what gives stars their spherical shape, what keeps them from simply dispersing into space. But when a star approaches a supermassive black hole closely enough, the black hole's gravity starts pulling on the near side of the star more strongly than on the far side. The difference in gravitational pull across the diameter of the star, which is what we call the tidal force, begins to stretch the star. At a certain critical distance, called the tidal disruption radius, this stretching exceeds the star's own self-gravity. The star can no longer hold itself together. It is pulled apart, torn into a long curving stream of gas by the differential gravity of the black hole. About half of this gas stream gets flung outward on hyperbolic trajectories and escapes the black hole entirely. The other half falls inward, eventually spiraling around to join an accretion disk or fall directly into the black hole. As this material spirals inward, it releases an extraordinary amount of energy. The gas heats up dramatically. It radiates intensely across a wide range of wavelengths. For months to years after the disruption, the region around the black hole can be brightened to a luminosity approaching or exceeding that of an entire galaxy. A single shredded star can briefly outshine hundreds of billions of other stars. These events are called tidal disruption events, and astronomers have now observed dozens of them. They are dramatic. They are violent. They are visible from billions of light years away. And yet the event horizon itself plays almost no direct role in the drama. The tidal disruption happens outside the event horizon. The radiation from the infalling material is produced outside the event horizon. What crosses the horizon is the final remnant of gas that made it past the point of no return. The fireworks all happen in the last few moments before that line. The event horizon just sits there, patient and permanent, waiting at the end of the process, collecting everything that finally falls through and letting none of it back. Tidal disruption events have become an important tool for studying supermassive black holes that are otherwise quiescent. A black hole that is not currently actively feeding through a large accretion disk is extremely difficult to observe directly. It produces no strong radiation. It announces its presence only through the gravitational influence on nearby stars. But when a tidal disruption event lights up the region around a quiet black hole, suddenly we get a detailed look at the black hole's mass, its spin, and the properties of its immediate environment. A chance to study the vicinity of an event horizon that would otherwise remain dark and silent. The event horizon, in other words, has a way of making itself known through what happens just outside it, even when nothing is actively crossing. Consider the deepest question the event horizon raises about the nature of space itself. Outside the event horizon, the 3 dimensions of space and 1 dimension of time behave in familiar ways. You can move forward or backward in space. You can move left or right, up or down. You can orient yourself in any spatial direction and move there. Time, on the other hand, flows in one direction only, forward. You can move through space in any direction. But you cannot move backward in time. Time has a preferred direction in our part of the universe. It is not spatially symmetric. This asymmetry of time is one of the most fundamental puzzles in physics. The laws of physics at the microscopic level are almost entirely symmetric in time. Run a video of 2 billiard balls colliding in reverse, and it looks like a perfectly valid physical interaction. Run a video of a building collapsing in reverse, and it immediately looks wrong. Something about macroscopic reality breaks the time symmetry that the microscopic laws allow. This is connected to entropy, to the second law of thermodynamics, to the fact that the early universe had extremely low entropy, and the universe has been increasing its entropy ever since. The direction of time we experience is the direction in which entropy increases. This is a deep and not fully resolved issue in the foundations of physics. Now cross the event horizon. Inside the black hole, the time-like direction, the direction along which time flows, has been redirected. What was a spatial direction toward the singularity has become the future direction of time. You might think of it as the time dimension and one's spatial dimension having swapped roles. Outside the horizon, you are stuck moving forward in time, but can move freely in space. Inside the horizon, you are stuck moving toward the singularity, but can move freely in what used to be the time direction. The physics of this is encoded precisely in the Schwarzschild metric, the mathematical description of the space-time geometry. The component of the metric that describes time and the component that describes the radial direction switch signs when you cross the horizon. Positive becomes negative and vice versa. The time-like direction becomes space-like and vice versa. This is not a metaphor. It is a mathematical fact about the geometry. What you experience as the inexorable flow of time, the thing that makes you older, the thing that connects your memories to your present, to your future, has been redirected inside the horizon. It now points at the singularity. All the properties of time that you take for granted outside, the way it carries you forward,